desire to find the Bode plots for this equation, 10k, we want to get that into this form, which is s over a number plus 1. So we need to convert this into 1. So to do that, pull out 10k, divide by 10k. So 10k times 10k gives us still s, plus, then it would be 1. And multiplying this out, you can see it's s plus 10k, and the quantity is the same here. So multiplying this out, this ends up being just 10. On the top are zeros, and the values on the bottom are poles. The roots of each of these is considered what's called a critical frequency. So a root on the top would be when s is 0, which is also at the origin. So there are 2 zeros at the origin. And on the bottom, the root of this is when s equals a negative 10k. When we're talking about frequencies, though, the negative is not a factor there. And so we're just talking about the frequency, which would be 10k. So we have omega at 10k, and the other one is going to give us omega at 1k. Both of these are poles. So doing the magnitude plot, for every 0, we're going to get a plus 20 dB per decade change. And for every pole, you get a minus 20 dB per decade change. So 20 times 2 would be 40 dB per decade would be the change due to this 0. And down here there's just 1, and so it would be minus 20 dB per decade change at 10k, and then again at 1k. So these changes happen right at these exact frequencies. So we know on the top that we're going to have a slope at 20 dB per decade until we get to the first frequency change, which would be at 1k. To determine where we're going to start the graph, we don't know what it is going to be at 0 because we plot things in dB, meaning that we can't actually find a numerical number at 0. So what we're going to do is find it at a different frequency, and then we can put the slope going through it as 40 dB per decade. So we're going to choose an omega that is less than all of our critical frequencies. In this case, we could choose 1, which is always an easy number to multiply and divide. And now we're going to find the magnitude when we substitute in j omega where omega is at 1. On the top, because this is only imaginary, and it actually ends up being j squared, so you'll just get a negative 10. The magnitude on the top, it doesn't matter that it's negative, the magnitude portion of it is going to be 10. So we're going to be left with 10 on the top, and down here to find the magnitude of this imaginary number, it's going to be the imaginary part squared plus the real part squared. When you have quantities such as this, you can actually multiply them instead of having to multiply them out. And multiplying these out ends up giving you approximately 1 on the bottom. Remember, this is plotted on a semi-log scale where the y-axis is in dB and the x-axis is either in frequency of hertz or in omega, which is radians per second. For a semi-log graph, the x-axis is a log and a y-axis is just normal, therefore semi-log. So a log looks like at every 10, it looks like it's evenly spaced. So at omega equals 1, 10, 100, these spacing between each of these multiples of 10, which is a decade. So a decade is any multiple of 10. they look like an even space. So now we can start graphing this. At omega equals 1, we know we have 10 volts per volt. We need to change that into dB. So to do that, it's 20 log base 10 of 10, which this will give you 1, so it's going to be 20 dB. So we can start off the graph at this point of 20 dB, where we have going through that point a slope of 40 dB per decade. So this slope here is going to be a 40 dB per decade slope. The value over at 10 then is going to be, since 1 to 10 is 1 decade, you can just add from plus 20, you're going to go up by plus 40. So this one's going to be plus 60. And then at 100, again, it's going to go up again by 40. So 60 plus 40 is going to be 100. And at 1K now, we have another change. So between 100 and 1K, it's again plus 40. So this value here is plus 140. And now at 1K, it was a pull, which means it goes down by minus 20 dB per decade. That means that I'm going to take the current slope value and add or subtract whatever changes there. So a plus 40 dB minus 20 dB gives a plus 20 dB change. And that will be constant until my next value in frequency is reached, where I have a change. So again, 10K has another change where from here to here now, this value is going to go up by, this was minus 40 plus 20. So it's a plus 20 dB per decade. So that slope is plus 20 dB per decade. So from plus 140 and going up by 20, because this is only 1 decade, I get plus 160 dB on the y-axis. So this point here is 160 dB. So now at 10K, I have another change of minus 20 dB per decade. So plus 20 minus 20 gives 0. So it flattens out. And the value all along here is going to be plus 160 dB. So what this says is that at 10K, my circuit begins to operate correctly, and it has a gain of 160 dB. And that will continue on because there's no change after that. The phase is slightly different. For every pull, your change happens 1 decade before the frequency to 1 decade after. And that is the region that the change occurs. The change for a pull is a minus 45-degree slope per decade. And for 0, it's a plus 45-degree slope per decade. For those that are at the origin, these give, remember this is j omega, so j is just an imaginary, and j omega squared is a -1, so that gives you a shift of 180 degrees. So the negatives do not affect the magnitude, they only affect the phase. So because we have 2 zeros, we're going to have a starting degree of a plus 180 degrees. The other times when you're going to have a different starting phase shift is if you have a negative, if you have a pole, you're going to get a minus 90 degree phase shift for every pole. So this one gives you a plus 90 degrees, and there's 2 of them, so you have times 2, and for every pole you would get a negative 90, and that's because you have 1 over j, which is a negative 90 degrees. So we start our graph at 180. Again, we have omega in radians per second, and on the y-axis it's in degrees. So I'm going to do my graph 1 decade before the lowest frequency. So 1 decade before 1K is 100. And 1 decade after 10K is 100K. So I actually like to mark it right here on the y-axis, the changes, and then I can add together all the changes that overlap. And this helps me keep them a little bit more straight. So I'm going to start with this one, which is the lower one. 1 decade before is 100, 1 decade after is going to be 10K, and the change between that range is a minus 45 degree slope per decade. Then there's the change at 10K, which starts 1 decade before and goes to 1 decade after. So between this region, I again get a minus 45 degree slope per decade. So here from 100 to 1K, I only have a minus 45 degree change. From 1K to 10K, I now have 2 that overlap. So this overlap is going to give me a minus 90 degree phase change per decade. From 10 to 100, I only have the minus 45 again. So my graph is straight at whatever phase shift I start at until I reach the first change region. So from here to here, I'm going to go down minus 45. So there's only 1 decade between 100 and 1K. So minus 45 off of 180 gives 135 degrees. Now from here to here, I have a minus 90 degree slope per decade. So I subtract off from 135 minus 90, I'm at 45 degrees. From 10K to 100K, I have just the minus 45 degrees. And after that, there's no change, so my line becomes flat again. So this point here, if I go down from this point to this point across 1 decade, it takes me down by minus 45 from 45. I end up with a 0 degrees at the end.